Quantum computing is a new and rapidly developing approach to computing that uses the principles of quantum physics to process information in a fundamentally different way from traditional computers. While classical computers use bits that can be either a 0 or a 1, quantum computers use qubits, which can be 0, 1, or a special state that is both at once. This allows quantum computers to explore many possibilities simultaneously, rather than doing them one step at a time. The result is that quantum computers have the potential to solve certain kinds of problems far faster than even the most powerful supercomputers today. Traditional computers are based on transistors, tiny on-off switches that represent bits. Every task your computer does, from loading a web page to playing music, is broken down into billions of operations on bits. Classical computing has been incredibly successful, but there are some problems that grow too large or too complex for even supercomputers to handle. For example, simulating molecules for new medical drugs, optimizing global shipping or airline schedules, factoring extremely large numbers for encryption, and searching massive solution spaces like certain AI problems. These problems grow at an explosive rate. A supercomputer might try millions or billions of combinations, but the total number of possibilities might be countless times greater than that. This is where quantum computing offers something revolutionary. Quantum computing is based on quantum mechanics, the set of rules that govern particles smaller than atoms. In this strange world, particles behave differently than they do in everyday life. They can be in multiple states at once, influence each other instantly over distances, and behave probabilistically rather than predictably. A qubit can be 0 and 1 at the same time. The computer can evaluate many possibilities simultaneously. Qubits can become linked, influencing each other instantly. This allows extremely fast coordination between qubits. Quantum states can reinforce or cancel each other. The computer can amplify correct answers and reduce wrong ones. These principles allow quantum computers to process information in parallel, rather than one step at a time. Imagine you're trying to solve a maze. A classical computer moves through the maze step by step, trying one path at a time. A quantum computer, due to superposition, can explore many paths at once. Then, using interference, it cancels out the wrong paths and strengthens the correct one, arriving at the solution much faster. Quantum computing is not about speeding up everything. It's about solving very specific hard problems faster. Some promising applications include drug discovery and chemistry, where quantum computers can model molecules accurately. This could lead to new medicines, vaccines, and materials like longer-lasting batteries. Modern encryption relies on the difficulty of factoring very large numbers. Quantum algorithms could break current encryption schemes much more easily. This is both a threat and an opportunity. It motivates the development of quantum-safe cryptography. Industries like airlines, banking, telecom, manufacturing, and logistics constantly solve problems involving millions of possible arrangements. Quantum computing may find optimal or near-optimal solutions much faster. Training large AI models involves exploring enormous mathematical spaces. Quantum computers could accelerate this dramatically and enable new kinds of machine learning. Quantum computing is still in its early stages. Today's quantum computers are small, often less than a few hundred qubits. They require ultra-cold environments and are prone to errors due to noise. They cannot yet outperform classical supercomputers for most tasks. We are in the stage similar to where classical computers were in the 1940s: experimental, expensive, limited, but rapidly advancing. Research is focused on increasing qubit counts, reducing error rates, improving stability, and developing better algorithms. Many major companies, including Google, IBM, Microsoft, Amazon, as well as universities and governments, are investing heavily in quantum research. Quantum computers are special-purpose machines, not general replacements. They will work alongside classical systems. Most everyday computing, playing games, browsing the web, office tasks, will stay on traditional computers. Think of it like this: classical computers are calculators for everyday use. Quantum computers are supermicroscopes for solving very specific, extremely complex problems. Despite these challenges, progress is steady and accelerating. Quantum computing is a new way of processing information that harnesses the strange but powerful laws of quantum physics. It doesn't simply make computers faster. It opens the door to solving problems that are impossible with classical computers alone. Quantum computing is like opening a whole new dimension of computing power, one that explores many possibilities at once, offering breakthroughs in science, medicine, technology, and beyond.